Hello, I'm discussing about factors affecting the relative strength of acid and base. First of all, effect of solving. The substance which exhibit their acidic or basic property in solution, the solvent plays very important role in the acidic or basic strength of such substance. Effect of solvent on the strength of acid in water, that is leveling effect. The tendency of water to equalize the strength of many acids or base termed as leveling effect. Hence, water is called leveling solvent. In aqueous solution, the extent of dissociation of acids depends upon the tendency of the water molecules to accept H plus, that is on the basic strength of water. Water acts as good base to our all common strong acids like hydrochloric acid, sulfuric acid. They are almost completely dissociated in aqueous solution such that all of them appear equally strong in aqueous solution. The strength of acid in acetic acid, that is differentiating effect. The solvent in which stronger acids ionize to different extents so that the relative strength of the acid can be measured are not differentiating solvents. For example, acetic acid is differentiating solvent and acetic acid is weak acid and it also behaves as a base to some extent. That is the same problem. In case of nitric acid and acetic acid, base solvent, therefore, even strong acid feebly ionized in this solvent, that is strong acid acts as weak acid in acetic acid. Effect of solvent on the strength of base in aqueous solution, the relative strength of base depends on the tendency of water to donate H plus, that is on the acidic strength of the solvent water. Water acts as a weak acid, that is acts as differentiating solvent for base. On the other hand, aniline acts as weak base in water appears to be strong base when dissolved in acetic acid as solvent. Effect of substitution on the relative strength of acid and base. The relative strength of acid and base is greatly influenced by nature of substitution, that is electron releasing and electron withdrawing group and their number present on them. Effects of electron releasing group on the strength of acid. Electron releasing group increases the electron density between S donor atom and hydrogen, which decreases the polarity of the bond. This hinders the dissociation of hydrogen and acidic strength decreases. For example, acetic acid is stronger than propionic acid and propionic acid is stronger than methyl propionic acid. Number of electron releasing group increases. Electron density between oxygen hydrogen bond increases. Strength of weights increases. Polarity of weights decreases. Rate of dissociation of hydrogen H plus decreases. Acidic strength decreases. Effects of electron releasing group on acidic strength. Let us consider the comparison of acidic strength of acetic acid, fluoroacetic acid, and difluoroacetic acid. Number of electron withdrawing groups increases. Electron density between OH bond decreases. Strength of OH bond decreases. Polarity of OH bond increases. Tendency of hydrogen dissociate as H plus increases. Acidic strength increases. Effect of electron releasing group on the strength of Lewis base. Let us examine the strength of flowing Lewis base. Basic strength. Number of electron releasing group increases. Electron density on nitrogen atom increases. Tendency to donate lone pair increases. Basic strength increases. Effect of electron withdrawing group on the strength of Lewis base. Let us examine the strength of flowing Lewis base. Number of electron withdrawing group increases. Electron density on nitrogen atom decreases. Tendency to donate lone pair decreases. Basic strength of Lewis base decreases. Steric effect. Trimethyl ammonium should be strongest base, but it is weakest base in above series due to steric effects. This electron donating capacity of nitrogen atom is hindered due to presence of trimethyl groups, and hence basic strength is very poor. Effects of electronegativity. Strength of acid increases if the electronegativity of the central atom increases. Let us examine the related acidic strength of the molecules, methane, ammonia, water, and hydrogen fluoride on the basis of electronegativity. Electronegativity of halogen atoms increases. Ability to withdraw electron increases. Polarity of halogen-hydrogen bond decreases. Tendency to dissociate S plus ion increases. Acidic strength increases. In the above molecules, hydrogen is covalently bonded to carbon, nitrogen, oxygen, and fluorine, whose electronegativity increases in the order. As the electronegativity of central atom increases, the halogen-hydrogen bond becomes more polar, and hence tendency to dissociate hydrogen as H plus ions from methane to hydrogen fluoride, so that acidic strength is the highest in hydrogen fluoride in this series. However, this rule is not valid for halogen acids, so relative acidic strength cannot explain on the basis of electronegativity because it gives opposite order. Atomic size of halogen atoms increases. Strength of hydrogen-halogen bond decreases. Rate of dissociation of hydrogen H plus ion increases, so that acidic strength increases. Oxidation state, the relative strength of oxy acids of element is determined by their oxidation states. Number of oxygen atoms bonded to chlorine increases. Electron withdrawing effects increases. Electron density between oxygen and hydrogen bond decreases. Polarity of OH bond increases. Tendency of the hydrogen to dissociate as H plus increases. Acidic strength increases. However, a series of oxy acids containing different halogen atoms but same number of oxygen atom, that is same oxidation state, their relative acidic strength is determined by electronegativity. that is acidic strength decreases if the electronegativity of halogen atoms decreases. Electronegativity of halogen atoms decreases, electron withdrawing effect decreases. Electron density between Weyer's bond increases, strength of Weyer's bond increases. Tendency of hydrogen to dissociate as S plus decreases, acidic strength decreases. Nature of bonding in boron trifluoride, though the partial positive charge on the boron atom is more due to the high electronegativity of fluorine, the tendency to accept a lone pair is reduced because of the ability of the fluorine atoms to donate their own lone pairs to the empty boron orbitals, forming p-pi back bonding. Fluorine forms the strongest backbone due to the effective overlap between the 2p fluorine and 2p boron orbitals. So the electron deficiency of boron gets compensated and the Lewis acid character decreases. But as the size of the orbital increases in the extent of back bonding decreases, this is due to the effective overlap as in case of 3p and 4p orbitals of chlorine and bromine respectively with that of 2p orbitals of boron. So the extent of back bonding is BF3, BCl3 and BBr3, and hence the Lewis acidity is highest in the BF3, lowest in the boron tribromide. This is the back bonding in the fluorine of the in the boron, p pi 3 pi, uh, p pi 2 pi back bonding 2 pi 4 5, 2 pi 5 5. Size of p orbital of halogen atom increases. Extent of p pi overlap between boron and halogen atom increases. Electron deficiency of boron atom increases. Acidic strength increases. In case of boron trifluoride, p pi back bonding is effective but not effective in the boron iodide. Thanks for watching. Thank you for your patience. That's now. Bye bye. So again.